think we should be good. So I'm Umayah. I work at Grammarly. I'm a software engineer on the data platform team where we build an internal data analytics platform. And I've been there for about 3.5 years. And I've been interested, throughout that time, I've been learning about big data systems and functional programming. So just a little bit about Grammarly. We're a writing enhancement tool that helps you write wherever you are on the internet. We're AI powered. Our goal is to improve your life by improving your communication. We have 4 offices, our headquarters in San Francisco, and around 200 employees worldwide. And we have about 20 million daily active users, and around 2,000 institutions use us through our business. And the main idea is that we help you write it. It's a writing assistant that helps you correct your grammar, clarity, engagement, and delivery. And we work everywhere that you write on the internet, whether it's on Chrome, your mobile app, or desktop, and Office add-in. And here's kind of a trajectory of since our inception of where we're at right now. Okay, so that's Grammarly. And what I do there is I work on an internal data analytics platform that allows our internal stakeholders to run reports on user interaction with our product, whether it's as you saw, we have 20 million users that use different products. They go to our websites, they download the app, they upgrade their accounts, and all these different events users are submitting. They come to our platform and we do some aggregations and transformations, and we allow users to run reports on that data. And it's called NAR because we're shredding the data. Yeah. So the goal of that thing is to support a few things: who our users are, how they interact with a product, and how do they engage, and how long they stay, stuff like that, and allows us to make data-driven decisions. And the way it works is we have this incoming data, we have this blob of our analytics platform, and we generate a report. And that analytics platform is built on top of Spark, and that's where kind of the inspiration of Iterators came from, because we're consistently dealing with iterators in Spark. It's like a core abstraction in it, and you have to constantly write custom iterators to do what you need to do, and it inspired this talk. So the idea was, I was inspired last year. I was listening to a talk that, they talk about key things, the essence of things we use on a daily basis that seem simple. And, Ariana Grande came out with that song, Thank You Next. And then I had this idea that iterators are one of those concepts where you use on a constant basis, but I wanted to deeply understand them. And preparing for the talk, it was kind of difficult because you have to come up with, it's hard to go through the fluff on the internet because it's kind of like a basic concept. So there's a lot of stuff that, you have to go through the fluff and kind of find that information that, you're looking for. And so sometimes you would search on the internet for keywords and you just throw Haskell or Scala or Monad in there, even though they have nothing to do with it, just to filter results. Yeah. So what are iterators? If we just decompose the word, iterators is, you have iterate and or. And iterate is to perform something repeatedly, and the or part is a thing that does something. So iterators repeat something repeatedly on something. And while that's the term that's used in commonly, Oleg, he came up with the Iterators. In an email archive, he was saying that the term iterators is not accurate, and the term cursor is more accurate. And he said that when you use a term of iterators, like the term that's used in C++, it's more as an accessor, and the iterator itself is not actually doing the iteration, it's just being iterated over. So it's not an accurate terminology. But that's a good analysis, but it's it's still used in common day, even though it's not accurate. So to kind of understand where the iterators came from, I kind of looked through different white papers and tried to understand where they came from. And you start around in like the end of the 50s and early 60s. That's when, a big time in programming languages and data abstraction, that's when they were actually being developed. The ideas of iterators, of abstraction, polymorphism, and the idea for, as you can see, IPL, this is an excerpt from IPL. So IPL and Lisp are some of they're the oldest Lisp processing languages. And the idea in IPL, they had a thing called generators, which, as you can see, it allows you to iterate, do something repeatedly on some sort of list. And IPL is like an assembly language. So in that language, they developed like a generator to do something consistently. They saw that they commonly had this need to do something consistently over some data or some collection. And IPL took like a more imperative approach, and then Lisp is, has a more functional approach, which is how they approached iteration and doing something repeatedly. And this is an excerpt from Clue. So Clue was developed around the 70s, and this is what they call an iterator, and they call it as a mechanism which incrementally generating the elements of a collection. And Barbara Liskov, who was a key researcher in data abstraction and polymorphism, the idea came from doing research with other institutions and looking what other languages like Alfred were doing, and they were impressed with they saw the Alfred approach and they thought it was a little too complicated, so they came up with their own form of iterator. And their form of iterator is more of a generator, which you would be familiar in Python. It's not an object-oriented type of iterator. And here's another expert from a paper by Stephen Watt. He also says something similar. And this is an expert from Essence of Iterator Patterns. And this is, I feel like, a great example, because what Jeremy Gibbons in this paper is trying to do is figure out how to do something that you can accomplish with iterators in a functional way. So to solve a problem that is commonly done in imperative world in a functional world. And programmers, we we just need to look at the type def. So you see in Scala, this is what iterator is. This is the definition of it, iterator. And the key idea is next and has next. That's probably what you guys are familiar with, has next and has next. It has state, it mutates, it's imperative. Okay. In reading all these papers, I saw different classifications of how people would look at iterators. One classification is control-based versus object-based. Control-based is kind of where iterators started with Clue and Alfred and different older programming languages. They started with control-based mechanisms for iteration, which are having in the language a form to iterate. It's a part of the language, it's part of the semantics of the language, a mechanism to iterate over the data, and it maintains the state for you, the state machine that's maintained for you. And something like this would be a yield in Python, the generator you saw in Clue. Those are examples of the control-based. And then object-based is, as data abstractions and polymorphism and inheritance were being developed in the 80s, and you saw people realize that you can actually do the iteration in the language itself, in the libraries of the language, not give it as a a core part of the language. Instead, you have users write libraries to do the iteration. And that's where object-based iterators come from. You encapsulate the idea of iteration in an object, and it maintains the state of the object, and gives you a minimal interface to go over some type of thing, whether it's a collection or even an API. Another thing you see is external versus internal. So external is like an object-based iterator generator where you're controlling the iteration, and it's in your hands of when to iterate and when to iterate next. And then the internal iterator is similar to a map fold, where you're passing something, and you're letting the programming language or the library do the iteration for you. You're not doing it yourself manually. And the nice thing about internal iteration is that it kind of reifies the transformation being done. You're passing a function, and you know it's going to be applied to a collection. And it can have cleanup code inside of it. You don't have to maintain this like opening files or closing certain things. It does that for you, but again, it's not as low level and gives you the powerfulness that external iterators give you, which gives you the ability to like defer the control of the iteration process and then process this later. Another one is, this is actually from kind of like C++ land, where traversal guarantees is what are you promising the user of the iterator? Are you promising just going once forward and then the iterator expires after that? Like a single pass algorithm only needs to iterate over a piece of data, a collection once. Or are you guaranteeing forward pass multiple times? Like a single linked list, you can pass over it multiple times. Some algorithms need to pass over data multiple times. Or going random access iterators, where you need random access. So these are iterators developed in C++. It's part of the standard library, the template library there, where they look at iterators and say, what guarantees do we want to give you? And state size is one way of looking at iterators, is how is the state within the iterator? Is it a constant state? Like if you're going over a sequence, that's constant state. If you're going over a binary tree, the state that you're internal within the iterator is proportional to the depth of the tree. So you have state iterators which can have dynamic state that constantly increases with the size of the collection, and you have iterators which have constant state. They don't need to maintain. They may only need to maintain one element, or even zero if it's like just doing some random number generating. And then you have the pull versus push. And this came about when they were developing reactive programming, or RX in C#. Eric Major saw that if you look at, you have iterators, which is like a pull-based approach. You're pulling the data. You manually pull the data and get what you want. And there's pushing. What's the opposite of pulling is pushing. Instead of pulling the data, can you push it? Can it be pushed to you? And there's the idea that iterators are the dual of observers, and a pull is a dual of a push. Here's the idea that these are the characteristics of, iterable is many. It's pulling synchronously. The idea of iterator is, relatively a synchronous thing, sequential synchronous thing. You do have async iterators in like C# and other languages. And but the main idea is that you're sequentially accessing data one at a time, and you're pulling it as you need it. Whereas the observable kind of switches that and says, you just push the data to it, and you have subscribers which subscribe to the data. And one way I thought nice of looking at it is that iterators, so you start with a value, but you end with nothing. And the opposite of that is you start with nothing and end with a value. And here's kind of that transformation. How they came up with that is that if you take this interface and by the way, this is a Scala Java kind of idea of iterator. And another way of implementing it is the C# way of iterators. It has its pros and cons, but one of the pros of this approach here is that the mutation and everything is happening in that one operation called move next, and then the current is not doing any mutation, so you have a kind of a better understanding of where the mutations happen, because here it's not clear if a mutation is happening in has next, and mutations typically do happen in has next. But here it's more clear that there's only one place where mutation happens. But if you take this and you just reduce it to just functions, all this is doing is all iterator is doing is returning you something of type A, and then you take that and you just reverse the arrows to get the dual of it. You get the idea of observers. And iterators, you can see, is covariant on type A, and when you do the dual of that, you get the observer takes the type A that's contravariant. And that's how and then from that you can make the interface. Once you take this core idea, simplified, then you can go back and make the interface of the observer. And that's where kind of the idea of observer and iterator were connected through this idea. And you can see that, and the idea here is that you can do anything you could do iterators, you can use observers. For observers, you can do iterators. They're dually each other. So you could transform one to be used like the other, and you could transform the other to be used like the other one. And that's kind of a cool feature. And depending on what you're working on, it's good to know that and know the different approaches to dealing with data. And you could add effects as needed. Here, if you want to, capture the idea, the effect of a null value or the effect of an exception, you would add it here. Scala doesn't do this. It's not, both for legacy reasons and mainly for legacy reasons. Also, when it was developed, probably it was boxing and it's not efficient. Since then, you have specialization, which would make this operation efficient, but for legacy reasons, you don't want to kind of try an option or any sort of monad or encapsulation in the core idea of iterators. In Scala, the core idea of iterator is it's a unit to a value. And, iterate any shape. Here's an idea of what iterators do with state. Here's a tree, you're iterating over this tree. You could iterate over sets, and the idea of iterators is you don't care what's there, you don't care what's behind it, you're just iterating over it. You don't care if it's a set, a hash map, anything, you just want to iterate over it. Your algorithm only cares to iterate over it. You don't care if it's a file, a black box, a database, a API, you just want to iterate over it, and it's this idea that it's a consumer, you have a consumer, and this iterator is this, barrier blocking you from knowing what's going on inside. And, if everything goes smoothly, everything should operate as you planned. But, you don't want to break this idea. You don't want to do stuff that is not guaranteed by the iterator or promise things that the iterator doesn't guarantee. You want to keep the iterator interface minimal as possible. Next has next. If you try to break this and do stuff or promise things that isn't guaranteed, you start to have problems. That's the problem with iterators, that they offer you a lot of power, but they have state, they're mutating, and they're kind of ugly to deal with in the real world. You could have a lot of problems. For example, if you have this example where you do some asynchronous computation and you wrap it in await that result. If someone's using this iterator, they'll be like, all I know is I could use this iterator and get data. But what if they call next to get data? Next time they call next, they have to wait. Then they have to wait. And then they have to wait. And they don't know this from the API. Well, this is Picasso when he was, on the left-hand side is when he was 15 years old, 25 years old, and then his 89 years old, his different ideas of a portrait. Here's another example. with iterators, there's no guarantee about how do you close resources, who handles the resources that you're opening. You could have closable iterators, but that still is not clear of where does that closing happen. And iterators are used everywhere. Databases, the query plan, which is in Spark SQL, is based off of they were inspired by the volcano model, which was that if you model a SQL query as a set of operations, select, scan, filter, you can combine those operations with the iterator-like interface, and you can go over the algebra of this with an open next, going through the operations like an iterator. This isn't used in the real world. Like when a Spark SQL, when you use data frames or actual databases, they actually don't do this iterator model because it's not efficient. You have vectorization and code generation. But the idea is still there. Even when you're making your own query plans, or expressions, you still kind of use the idea, but then you optimize it later. It's core abstraction in Spark. When you're dealing with Spark, you're kind of at the core of it is this iterator model. Also with Kafka, Cassandra, when you're reading data, when you're doing certain things, you're given an iterator and you're using an iterator API, which is kind of with the example I gave of having await.result. Sometimes that's not, sometimes you have to be forced to do something where you're dealing with an asynchronous source and a synchronous API where you have to do something ugly. Sometimes Spark makes you do some ugly stuff with that you want to map a partition, you're given an iterator. You're not given some asynchronous thing. And programming languages, every programming language has their different idea of what iterator is. This is the API of Scala. In 2.13, they revamped it. They got rid of the traversable and they made it simple with iterable once. And every iterable once outputs the iterator, and it underlines the collection library in Scala. So basically all Scala collections are internally using iterators. If you look at the API, if you go through the library, iterators are used everywhere in Scala collections. For example, all these operations, filter and flat map flatten, are used internally. If you look at the operation, they're using iterators to do the operations. All collections give an iterator, use iterators internally. There are exceptions like lazy lists which do not, but the vast majority are using iterators internally. One thing nice about iterators is that they compose, and they are composable, but they also fuse operators, which isn't what you get with normal Scala collections. Scala collections, while they use iterators internally, every time you do a map, it outputs a new iterator. Then you do it again, it outputs a new iterator. And instead of doing this operation multiple times, whereas iterator, you're morphing the transformations together. You're fusing the operations together because you're operating one element at a time. So you can fuse it one at a time. You can get this functionality if you do seek.view or seek.iterator. You'll get that functionality, but at the core collections, purposefully don't do this. They don't fuse operations, and that design was purposeful. For example, here's the iterator. You map. It's going to return another abstract iterator, and they use abstract iterator as a stub method so that you don't have this huge class files. But the idea is you map, create an iterator, and then you do map again, and it'll just wrap the previous next, and you create that. And you just keep doing it, fusing these operators. Scala iterators, flexible, efficient, sequential, same thread. And in Grammarly, we use iterators all over the place. We have an isLast iterator, do something on the last element, kinesis, shard iterator. We use kinesis in kind of like a synchronous way where we have to prefetch data and then serve it we're feeding it to Spark, so that's where we have to force it to be synchronous because we're doing some batch processing where we need the kinesis API, but we want to feed it to Spark in a batch-like matter. show that later if I have time. Merging tuple, query iterators. You know, we have internally, we have different types of iterators for our queries, like when we like embed an algorithm inside the iterator. And iterators are just basic container. Let's say you want to generate 0 or more values. You can use an iterator. You just want a base minimum API. I have little time left. Let me quickly. So functionally, they came up with ideas of iterators. You have Iterate. And the idea is that you're funneling data, kind of just like a plumbing example used by Oleg, who developed the idea of Iterate. And you're able to have this iterate and enumerator. Enumerator generating objects, and the iterate is like the stateful, this no state. It's immutable thing that takes this data stream and does some operations over it. So that's kind of ways in the functional world you want to do these abstractions. You want to do iteration, but you think about it differently. You would do it in a different fashion. Here's an idea of how it works. I could share this later. And you have applicative functors, which was developed by Essence of Iterator pattern, where the applicative functor, the traverse operation, kind of encapsulates this idea of iterators. You can see it here, this tree, and it's composable. It's you can compose different, and you can do both accumulating and mutating behavior. And the idea is that iterators have this idea of accumulating and mapping. How do you do that in the functional world? You can use applicative functors. They solve that issue. And this was actually recently. I mean, it's not recent, but like in the 2000s, like 10, 11 years ago, this kind of ideas came about. For like 40 years, we've been using this like stateful imperative way. And then here comes more functional approaches. In the future, there'll be more and more ideas of iteration. But basically, the idea is iterators are a fundamental concept in programming, and they solve issues, but anywhere you can use iterators, you don't have to use them. You can use a functional approach. That's the core here. The idea is that you don't need them. They're nice to use, but there's also functional approaches to it. There's different, if you change the way you view it, the problem, you can solve it in a different way. And I think we're running out of time, but I want to show some code examples, but maybe if anyone wants to see it, I can show you later. And Grammarly, we're hiring here, but I wanted to show, hopefully I can. Okay, so here I wanted to, just show the, start with the iterator interface. Okay. It's not working here. Probably show that for whoever is interested, but that should be it. Any questions? Yeah.
Much. Do we have any questions? Oh.
Thank you for a great talk. Umayah, I have a question. It's great to have Grammarly for the first time presenting. We all know this as a product, so it's exciting to see there is Scala inside of it. I just wonder how we found that NLP people like Scala. A lot of research and development is done on it. So I wonder if there is something about that appealing to human language geeks and programming language geeks. How is it evolving inside Grammarly? Can you tell us a little bit about like how adoption happens? Is it something people pick up? Is it something which is kind of coming from the top? How does the culture enable kind of interesting programming language learning and education and adoption?
So if you're talking about the programming language in Grammarly, so a lot of, so we're very functional, we love functional programming in Grammarly. Multiple teams use Scala, but also multiple teams use Clojure and Lisp. And we try, also interestingly, Java, reactive programming in like, when you're doing reactive and also in JavaScript, we have we built functional libraries in a functional manner in our front-end extension with JavaScript. And kind of it's kind of ingrained in the culture to use these higher level abstractions in programming to make a better product. We've noticed it makes the product better, it makes lives of engineers better, and it offers engineers a nice, something that they're interested in doing. You don't want to be stuck with this imperative world.
Hi. This might not be directly related to it, but have you considered applying the principles of machine learning, et cetera, to help programmers write better code as well?
The essence of Iterator? Are you talking the essence of Iterator pattern?
I'm sorry?
Which one were you talking about? Oh, can you repeat?
I mean, Grammarly helps with grammar and word choice and stuff, syntactic, help like that. I was wondering, can that be applied to writing programming language programs?
That's so I think so the idea of it's more, I think I don't think they're correlated. Like the ideas behind the natural language and programming languages are kind of far apart, so they can't really be applied in the programming sense.